Okay, okay, for this problem, we're looking at a Fourier series representation of a periodic input voltage, okay, given by the equation Vn of t. And what we want to know is what is the output with this input when it is applied to an ideal low-pass filter, an ideal band-pass filter, and an ideal high-pass filter, okay? So what we want to do is start with some observations, okay? Now we know that the DC component here is when omega equals 0. Okay, and we also know that the frequency there will be omega over 2 pi, which of course is 0 hertz. Okay, now for n equals 1, okay, we know that omega will equal 4 pi based on this equation here. And our frequency will be omega over 2 pi, which is 4 pi over 2 pi, which is 2 hertz. All right, then we're going to look at n equals 2, all right, and we know that omega will equal 8 pi, and the frequency will be omega over 2 pi, which is 8 pi over 2 pi, which equals 4 hertz. Okay, so that gives us a general trend of what's happening during our frequency. So let's look at a low-pass filter, okay, and what it's defined for us as is it has a cutoff frequency, FC, of 3 hertz, okay? So what does that look like? Right? Remember, we're dealing with an ideal low-pass filter. All right, and so our pass band is here, and our stop band is there, which means in our pass band, that's where the signal is going through. So if we apply that input, we know that everything below 3 hertz will get through, and everything above 3 hertz will be stopped. So since we developed some intuition about what's happening with the signal, we know that when n equals 2, our frequency is 4 hertz, okay? And so that will not make it through. So that all that makes it through to the output is our DC component at 0 hertz, and our first component, where n equals 1, okay? And so that is our V out. So the next thing that we want to do is to look at a bandpass filter. And for this problem, it's letting us know that our first cutoff frequency is 9 hertz, and our upper cutoff frequency is 11 hertz. Okay, so again, let's draw what this looks like so we can get an intuition for it. Okay, so this is 9 hertz, this is 11 hertz. And again, this is our pass band, this is our stop band. Remember, anything outside of the pass band cannot get through. All right, so if we again pay attention to our omega c, it's 2 pi c1. Okay, so when that is 9 hertz, means we're at 18 pi. And remember that our omega was 4 pi. Okay? So n equals 4.5. Okay? So similarly for the other cutoff frequency, which equals 22 pi. All right, and so here n is 5.5. So what this is telling us is the only signal that's passing is when n is between 4.5 and 5.5. Now we only do integers of n, so that only leaves us n equals 5. So when n equals 5, we can say that our V out is going to equal -1 over pi sine 20 pi t volts. Now we got that because all we did with our original signal here is set n equal to 5. Okay, so that is V out for our bandpass filters with those two cutoff frequencies. The last thing that we want to do is a high pass filter. Okay, and we are given for this high pass filter that the cutoff frequency is 5 hertz. Okay, so if we drew a high pass filter, we know that everything above 5 hertz is passed and everything below is stopped. So finding what that means for our frequency means 2 pi 5 equals 10 pi, which is equal to 4 pi from our original equation, and n is going to equal 2.5. Now again, we're only dealing in integer multiples of n, and so that means everything above n is 3 will pass. Okay, so our V out, okay, we have to keep our original equation because we're going to do everything above n equals 3. And that is our V out. Okay, so what we did is we figured out what our signal was and what that meant for when it was applied to ideal filters, a low pass filter, a band pass filter, and a high pass filter. That's all.